Okay, so let's start with this. In this video, we're going to look at classifying differential equations. Now, first of all, let's understand what a differential equation is. A differential equation is any equation, obviously. So, obviously, the first thing it's got to have is an equal sign. And on some side of it, you may have a derivative. For instance, here, dy dx plus y equals 2. This is a differential equation. So, you can have any differential equation that anything that has a derivative in it is considered a differential equation. So that's the first thing. Now, differential equations, of course, require us to integrate, usually because they are the reverse process of differentiation is integration. Now, as you would have done in Calculus 1 or 2, you've seen that integration can be quite challenging, and therefore integrating and solving differential equations is quite difficult. Now, when we say solve a differential equation, let's understand what a solution is. A solution to a DE, let's call it a differential equation, is when you eradicate the different derivatives. So in other words, you have to remove the derivatives using integration or some other technique that involves integration and come up with an equation. In this case, for instance, here we're looking at y as a function of x, for instance. So you get an explicit or implicit solution in y and x. So in other words, you're looking at some function of y equals some function of x. And this equation does not contain any derivatives. So when you get to that stage, we say that we've solved the differential equation. So what is it? It's simply take the equation that contains a derivative and remove the derivative from it with a mathematical process such that you end up with no more derivatives in the equation. Now, if you have higher order derivatives, then you must perhaps repeat the process or find a process. In any case, all the derivatives must be removed. Okay, let's move on now. Now, solutions or solving differential equations can be quite challenging, as I said, because the base or the root of solving differential equations comes from integrating, and integration can be quite challenging, as we've seen. So, it is very important to classify differential equations because classification helps us to figure out what techniques will work and what will not. Okay, well, first of all, there are two types of differential equations. There are ordinary differential equations. There are partial DEs. So that means that if the equation contains a partial derivative, we call it a partial DE or a PDE. Okay, and if it contains only the standard complete derivatives, we call it an ODE, or an ordinary differential equation. Now, this particular video and the subsequent videos will be considering only ODEs. So let's move on. So within ordinary differential equations, in fact in PDEs also, both cases, we have what's called the order. So the order is basically the order of the highest derivative. Now, you all know what order is, hopefully. So this is first order derivative, this is second order derivative, this is the third order derivative, and this continues on, and you have an nth order derivative. Okay, so this number here indicates the order. So the highest order derivative in any equation, in any differential equation, defines the order of the differential equation. So for instance, an ODE that contains a second order derivative, we call it a second order ODE, if that's the highest derivative. One that contains a third order derivative, we call it a third order ODE. So that's what order is. Okay, let's move on. So after order, so the next idea is linearity. Now, linearity, when we look at a differential equation, you can think of it as some function of different order derivatives. So it contains an equation in y and x, for instance. It would contain xy. It would contain dy dx, for instance, d2y dx squared. Okay, and so on. And it can contain n derivatives, nth order derivatives, and basically that equals 0. So that defines what the structure of a differential equation is. Now, what makes it linear or non-linear is how, not x in this case, not the independent variable. We don't care how the independent variable occurs in the equation. So it's not important. However, all of these, all of the derivatives and y itself, which is the dependent variable, and its derivatives must occur linearly in the equation. What we mean by that is you cannot have a y that is squared, cubed, or anything nonlinear, sine y, cosine y, tan y. Okay, so y squared, so nonlinear equations, it's nonlinear if there's a y squared or a sine y or a cosine y or an exponential y, ln y, because these are all nonlinear functions, okay? And any versions of these. Now, and the same thing happens if you have dy dx or any of the derivatives squared or sine of dy dx or cosine of dy dx or so on. So any nonlinear occurrence of any of the derivatives. Now I'm just showing you the first. That can be the second, third, fourth, fifth, sixth, nth derivative. Any of these derivatives, if they occur in this form, we say that the equation is nonlinear. And only one occurrence is sufficient to make the equation nonlinear. And of course, it should not be reducible by some algebra where this can be removed, this square, for instance, or something. So therefore, this kind of form has to stay in the equation. So here will be a quick example of nonlinearity versus linearity. This is so if I said dy dx, y dy dx plus x y cubed equals 0, then that's a nonlinear differential equation. Okay, if I had, for instance, d2y dx squared plus y dy dx plus x squared equals 0, that would be a nonlinear differential equation. Now this would cause the nonlinearity, and so would this. In this case, this would cause the nonlinearity because y and any of the derivatives cannot multiply each other because that is a nonlinearity in the dependent variable. Okay, so now that you have a reasonable idea, hope, of what is linearity versus nonlinearity. Now, linear equations, let's look at a quick example. Here's an example of a linear equation. Now, what's the order of this? It's a second order differential equation. Clearly, that's the highest order. It seems to be. So dy dx plus y equals exponential x. Now look at this. We don't care about the exponential, or x, I mean. The exponential is of x, and therefore does not affect the linearity of the differential equation. But look at this, it's y alone, dy dx, and d2y dx squared, so this is a linear. This is a linear ODE, and the highest order derivative is 2, so it's a linear second order. Okay. Now some people like to define what's called a degree. It's not common, but a degree is the power, the highest power of y, or its derivative. Actually, highest power of the derivative. Okay, in this case, that's degree 1. Okay. Okay, so a homogeneous versus a non-homogeneous ODE is one where if you collect the y's, the functions of y on one side and take the functions of x on the other side. So in other words, if you have f of y dy dx, d2y dx squared, and higher derivatives, okay, you take all of these and then you have some g of x on the other side. Now, such a differential equation, okay, first of all, when we look at the concept of homogeneity, we're looking at linear differential equations, okay? So we're looking at linear differential equation. So this is a subclassification under linear differential equations, all right? So we're assuming this is a linear ODE. Okay? We're assuming it's a linear ODE. Now, if gx is equal to 0, we say this is a homogeneous. This is a homogeneous ODE. Homogeneous ODE. And if gx is not equal to 0, then of course, clearly, that's the only other possibility, it is a non-homogeneous differential equation. Okay, let's move on quickly and see examples. Let's look at a quick example here. Here's one. So if you look at this differential equation, what is the order? This is an ordinary differential equation, of course. It is third order. It's third order, and it's linear. And of course, it is non-homogeneous. Now, every differential equation that is non-homogeneous and linear has a homogeneous version. So what would be the homogeneous version of this example here would be just to look at the left-hand side and make the right-hand 0. Now, of course, it's not the same function. We'll call it, say, y1, okay, or yh, which means y homogeneous. Okay, so every differential equation that is linear has a homogeneous counterpart. All you have to do is ignore the right-hand side for the time being and proceed with that. There's one more idea in the classification of differential equations, and that is, in fact, the coefficients of the differential equation. And again, we're sticking to linear differential equations. Within linear differential equations, there is another subclassification, and that is constant versus non-constant coefficients. So constant and non-constant, or variable. And constant and non-constant coefficient. What I mean by that is as follows. Of course, these are not in y. What this means is, for instance, you have dy dx, okay, plus y equals ex. Now, this is a first order ordinary differential equation. It is non-homogeneous. It is linear. Now, it has constant coefficients, because if you look at what is actually here, 1, and what's here as a coefficient of y is 1. So when we say coefficients, first of all, we have to understand what is a coefficient of a differential equation. The coefficient of a differential equation is the multiplier, is whatever multiplies the y term, the y or its derivatives. Anything in the equation that multiplies y and its derivatives is called the coefficient of the differential equation. Now, as you see in here, the number 1 is multiplying. Now, I could change this into another example. Here's another example. If I just alter this, 2 dy dx plus 3y equals ex, see, these are still constants. So this is a first order linear ordinary differential equation. It's non-homogeneous, and it's got constant coefficients. Here's another example where I could have, for instance, dy dx plus x squared y equals sine x. Now here you will notice that there is a non-constant or variable coefficient. Identify this one is first order ODE. It's linear. It's non-homogeneous, and it's got constant coefficients. And that's its classification. This one, on the other hand, is again first order. So they're all first order, actually. So this is first order, this is non-homogeneous, and it's also got constant coefficients. So I'm just going to say constant coefficients. Okay? And this one has variable coefficients. Okay? This one's got variable coefficients. So that's it on classification. That covers all the aspects of how we classify differential equations. So again, just to quickly recap, within ODEs you've got linear, and then you've got nonlinear. Once it's nonlinear, the only thing then after that is order. It's irrelevant. Okay, so here you can calculate order. Other than that, there's nothing. Here you have order. Okay, and then you have also within linear you have homogeneous, say, versus non-homogeneous. Okay, and then you have constant and variable coefficients. Okay, so you've got these under linear. You've got these three subclassifications. You've got your order, you've got homogeneity, and you've got your variable versus constant coefficients. Okay, and under nonlinear, the only thing you can further do is you can just calculate the order. I mean, you don't have to have it nonlinear to identify. Order can be identified at the start. It's not affected by linearity.